Okay, this is one of the most important videos I've recorded lately, and it's about prompt engineering, optimizing prompts, and whether or not it's a waste of time. This is a very interesting research that I found. It's one of the most well-structured research that I've seen lately about prompt engineering, and the whole idea in this research is to test how efficient are different prompt engineering techniques such as chain of thought, zero-shot prompting versus few-shot prompting, etc. And specifically for software engineering tasks. So these research results are pretty surprising. Before I dive into this research, let me give you a bit more context. So many of you who are using AI coding assistants are trying to, and including myself, we are trying to optimize our prompts because we were taught and we saw different researchers that say that the prompts are very important. I actually built a tool for saving prompts that allows you to save like your top performing prompts. It's called Prompt Superfast, but never mind, we won't dive into it. Anyway, so many of us also tried to give custom instructions to our AI coding assistant. So if you're using Cursor, you have the Cursor rule file. If you are using Claude, aka Klein, you give like the custom instructions. And there are many discussions also in the Klein Discord group and also in the Cursor forum about what is the best custom instructions that you provide to your AI coding assistant in order to generate the best results. And I also did a few videos about these topics, and I also experimented with different custom instructions very often. This is the reason why I saw this research. I found it very interesting and also quite surprising. So let's dive into the research. I will share the link to the research in the show notes, or more precisely in the video description. So basically their goal is to figure out is whether do advanced language models eliminate the need for prompt engineering in software engineering. So this is the question. Now I did like a summary using Claude over here. Let's remove Klein. Okay, so overview. This is the first comprehensive study evaluating prompt engineering techniques on advanced LLMs for software engineering tasks. It focuses on code generation, code translation, and code summarization, and it compares different prompt engineering techniques and performance of non-reasoning models, in this case GPT-4o, versus reasoning models O1 Mini. And it evaluates the effectiveness, the cost, and practical implications. Now, they had three research questions. So first of all, are previous prompt engineering techniques effective for more advanced models? This is, I think, the most important question we should ask ourselves because, again, we were taught that we should write very detailed prompts with the role, with examples, limitations, constraints, structured output, a lot of this stuff. So whether or not it's relevant, then they asking or researching what are the advantages / limitations of reasoning LLMs versus previous models, and how should we as practitioners select techniques and models considering the costs involved. So again, they use two models, GPT-4o, which is a non-reasoning model, and O1 Mini, which is a reasoning model. 3 different tasks: code generation using the human eval dataset, code translation using the code trans dataset, and code summarization using the code searchnet. By the way, before I move forward, obviously this is just one research, so even if the results are surprising, but obviously there are limitations to any research. Let me just get this disclaimer out of the way, because many of you might say after viewing this, oh, but this is BS because they didn't do this and they didn't do that. So obviously you must take the results of this research with a grain of salt. Anyway, so let's just go over different techniques of prompt engineering just cover them very fast to give you context for those of you who are not really remember all of them or don't know. So first of all, we have zero-shot prompting, which is the most basic type of prompting. Basically, you ask the LLM to perform a task. You don't provide any examples, no specific or special formatting. This is what is used as baseline in most studies. And an example would be, please generate a short comment for the following function, and you just add the code. And this is simple and uses minimal tokens. It's quick to implement. This is what we usually do on the fly. And the cons may not provide enough context and lower performance on complex tasks. The next type of prompt engineering technique is few-shot prompting, which is also known as in-context learning. We basically provide an example of input and output pair before the actual task, and it helps the model understand what is the expected format and the style. So here's an example. Function. This is the function, this is the comment, this is the function, this is the comment. And now we asked it to now please comment this function, and we add the function, and then we obviously expect it to add the comment. And because we provided these two examples, usually the LLM is going to provide us the correct output format and style because we provided examples. So some prompt engineers, they provide like 5 different examples. Obviously, it provide more preciseness and accuracy, but on the other hand, it's going to be more tokens. It might confuse the model. So a few downsides for that as well. So the key considerations is how many examples do you add, typically between 2 to 4. What are the examples that you provide? It must be relevant to the target. And what is the order of examples? So if you provide, you're just going to get different output based on the order of examples that you provide. This is also something to keep in mind. The pros, it helps the model understand expected format. It improves performance through examples. The cons, it's used as more tokens, and example selection can bias the output. Now, the next prompting technique is called chain of thought. Basically, it guides the model through intermediate reasoning steps, and it breaks complex problems into logical segments. And this is specifically useful for complex reasoning. So, for example, please solve this problem step by step. First, understand what the function should do. Then, identify the input parameters and return type. Next, plan the algorithm. Finally, write the code implementation. And this is the placeholder for the problem. The pros, it's better for complex problems requiring multiple steps, and it improves reasoning quality. It's more expensive. The cons, it's more expensive in terms of tokens, and sometimes it's going to be unnecessary for simple tasks, so it's just going to take more effort to generate. Although we can use a prompt expander, but this is a different topic. Another technique is expert prompting. Basically, we begin with describing an expert persona. We tell the LLM exactly what is like his skill set, and we'll see an example in a moment. So you set the context for expertise level and perspective, aims to improve output quality through role playing. So an example would be, you are an expert software engineer with 10 years of experience in Python development and best practices for writing clean, maintainable code. You excel at writing clear, concise documentation. Please review and comment on the following code. And the code is here. The pros and cons, it can improve quality by setting high standards. It helps maintain consistent perspective, very important. It may not impact performance for simple tasks, and it's additional tokens overhead. The next, it's not exactly a prompt engineering technique, but basically having multiple agent approaches. So you use multiple LLM instances as different specialists. We can just assign different LLMs or different roles for different agents. We also have the approach of the code architect and the code executioner. So different ways to structure this. So basically each agent has a specific role, and it enables comprehensive problem solving. Here's an example. So there is the analyst who understands the requirements. We can also attach it to a specific knowledge base, give it specific prompts using the prompts that we mentioned before. Then we have the programmer who writes the code, we have the tester who verifies the codes, and we have the reviewer who suggests improvement. And this is an example. The pros and cons, it's a comprehensive coverage of different aspects, specialized handling of each task component, which sounds like it pretty, sounds very useful, especially, I mean, every time I do a video about this kind of topics and mention specialty, I think about the quote by Adam Smith, the famous economist, who said that society basically advances by specializing. So yeah, quoting Adam Smith, check. Okay, so the cons of this, it has higher complexity and cost, and it requires careful consideration. And we have iterative refinement, which is again, I wouldn't say it's exactly a prompt engineering technique, but it's mostly like a way of interacting with the LLM until you get what you want. So multiple rounds of generation and improvement often includes feedback from execution or testing. So feedback is having a human in the loop, or just fetching the errors from the console, or fetching the errors from the problems, or whichever errors arise. So, and it focuses on continuous improvement. The feedback types are runtime errors, test case results, performance metrics, code quality metrics, etc. The cons, it can't produce higher quality, the pros, it can produce higher quality results, it handles complex edge cases better, it's more expensive, and it just takes longer. Now, so we got that out of the way, and we now know the different prompt engineering techniques that were tested in this research. Now let's move on. Maybe let's move on back to this research paper. Let's just cover the different research questions. So the first question they checked is, are previous prompt engineering techniques effective for more advanced LLMs? Okay, so existing studies on LLM-based code-related tasks in software engineering have predominantly utilized earlier models like ChatGPT 3.5 and GPT-4, which are now outdated and no longer supported by OpenAI. Recent evaluations have shown that approaches based on these earlier LLMs sometimes underperform compared to more advanced LLMs that are utilized without specific prompt engineering technique. Advanced models trained with higher quality data and more robust training strategies may exhibit reduced sensitivity to prompt engineering techniques. Specifically, models that have chain of thought reasoning. So this raises the question of whether prompt engineering techniques remain necessary to enhance performance in such advanced model. So this is the first research question. Let's cover the results instead of going over all the questions. So the key findings. So I won't make this video too long. So if you want to read, see exactly what were the results for each prompt engineering technique and each model, you can check out the research papers. They also have a really nice visual representation with tables. But the finding was, first of all, for non-reasoning models, GPT-4o, prompt engineering still helps, but then benefits are reduced. So execution feedbacks are more important than prompt formatting. So this is, I wouldn't say it's obvious, but it's important. And performance gains are smaller compared to all earlier models. Now, this is fine, but it's not as surprising as these findings. So for reasoning models such as O1 Mini and O1, simple zero shot often performs best. It performs better than using any of the other prompt engineering techniques. So this is why I think this video is so important, because if we are building using Klein and we are taking these custom instructions from Corsair directory or from the Discord channel of Klein with the custom instructions, usually the custom instructions are very long and they seem very comprehensive, but when being tested here, we see that actually zero shot often performs best, and complex prompts can hinder performance. So this is crucial. And built-in reasoning reduces need for elaborate prompting. So this is very important. And let's check out table 2. I wrote myself to take a note of table number 2. Let's go to table number 2. Okay, so this is table number 2. So performance comparison of different approaches in code generation. So we have GPT-4o. This was the result in zero shot, chain of thought, agent coder, which is like the iterative, as you can see here. And for O1 mini, we have zero shot, chain of thought, and agent coder, self collaboration, and LDB. Never mind, these are just different techniques, but the gist is what I shared with you. Obviously, I recommend that you dive into this more deeper if you're interested. Now let's move on to the next research question. So what are the advantages and limitations of reasoning LLMs in software engineering tasks compared to previous LLMs? Building on results from the first research question, this question seeks to explore the specific conditions under which the reasoning model outperforms non-reasoning models. Given the diversity of software engineering tasks and scenarios, it is essential to determine the type of data and tasks where the reasoning models excel and where they may encounter difficulties. By investigating these factors, we aim to provide a comprehensive understanding of the reasoning model's strengths and weaknesses in the software engineering domain. So sometimes O1 mini reasoning models underperform or perform not as good as the non-reasoning models, and this is something that is also very important for us to take into account when we are building code. So let's see the key findings. Okay, so complex reasoning models excel at complex tasks requiring multi-step reasoning, problems with chain of thought lengths higher than 5 steps. This is also very crucial, and where we have self-correction through internal reasoning. Reasoning model limitations, so excessive reasoning for simple tasks. When you have a simple task, you shouldn't use a reasoning model. When you have a less structured output format, it's also not good for the reasoning models. And obviously we have the obvious downside, which is higher computational cost and longer response times. Just using O1 mini is going to be way more expensive and way slower. So this is also something to keep in mind. Now moving on to the third research question is, how should practitioners and researchers select prompt engineering techniques and foundational LLMs considering the monetary expenditure and time cost? So OpenAI pricing indicates that reasoning LLMs have significantly higher costs and longer API response times compared to non-reasoning LLMs. Moreover, due to the model autonomous reasoning phase, which users cannot directly control because we just give it a question and then it takes, 10 seconds, 25 seconds in order to do like the thinking, we don't have control of what's going on behind the scenes. Therefore, this research question aims to evaluate the balance between cost and effectiveness in software engineering tasks, providing recommendations on when and how the reasoning LLMs should be used in practice. We aim to offer practical guidance for practitioners and researchers make informed decisions regarding the adaptation of advanced LLMs in cost-sensitive context. So here's a table with a summary of prompt engineering techniques utilized by each approach. This isn't what I wanted to share with you. So here's like the findings of this research question. O1 mini uses significantly more tokens. We knew that. Reasoning tokens can be up to 18x than message tokens, and complex prompts increase cost substantially. Time cost, O1 mini takes longer to process. Multiple iterations compound time differences. Higher costs don't always mean better performance. So this is very important. So the practical recommendation, this is kind of like the bottom line, which is more elaborated if you read the research. So when to use non-reasoning models, GPT-4o. Simple task, chain of thought length is smaller than 3 steps. Tasks requiring concise output, cost-sensitive applications, natural language generations for software engineering tasks, when to use reasoning models, complex tasks when the chain of thought length is higher than 5 steps, when deeper reasoning is necessary, use with simple prompting techniques. This is also very important, simple prompting techniques. When using reasoning model, there is no need to use the role-playing, or no need to have few shots with examples, So, and you should include output format restrictions. I won't share the research directions. I guess that's almost it. I think this is one of the reasons why this blog, why this research by the Aider team is so important, because what they did here is basically they separated the code and the reasoning to two different models. An architect model, which is asked to describe how to solve the coding problem, let's say a reasoning, so O1 or O1 mini, and an editor model, which is taking the architect solution, which is broken down, let's say for steps that are less than three steps, because we saw that is the best practice. And he actually executes the code. And this is like a comparison that he did for different coding tasks. And you can see here, this is the architect model, the colored, and these are like the execution models that were used. So as you can see here, with O1 preview as the architect and DeepSeek as the executioner, the pass rate, it was 85%. With only O1, the pass rate was 79%. Same with Claude Sonnet, when Claude Sonnet was the architect and also the executioner. So still the code was divided to two different LLMs. The results were better than when only using Claude, with no separation between the coding architect and the coding execution. And this aligns, I wouldn't say 100% aligns. I need to think about it, whether or not it 100% aligns, but it somewhat aligns, or there is a big correlation between the findings here and the findings in this research. And I think this research is like really crucial, because from now on, I'm not sure that I'm going to use like the so comprehensive custom instructions. It's probably, it might be just a waste of time and tokens. And it might be way better to have like these simple prompts and just providing more context, or making sure that we give more detailed instructions on the fly and share like the errors while we are iterating, because I saw in the research, and if you're going to check out the research as well, you will see that the iterative process is one of the most impactful things that you can do in order to generate better code. So this is way more important, I think, based on this research. It's more important than fine-tuning the custom instructions. And there are actually downsides to fine-tuning the custom instructions and making it very long and detailed. And this is definitely something that should be taken into account. Yes, I guess that's it for today, guys. I hope you enjoyed this video. If you did, please like, comment, and subscribe. Obviously, if you have any ideas, anything that you stumble upon that you think can be interesting to cover, or any suggestions regarding this type of prompt engineering, please share them in the comment section. And until next time, keep on automating.